So, any questions? All right, so let's sort of pick up where we left off. We have box on cliff. I'm going to take this one through the entire process, even though we're primarily concentrating on the force diagrams at the moment. I broke this down because partly when you're first starting out and trying to figure out how you actually break it down, what do I need to do forces on it? It's not necessarily obvious to everyone about how it's supposed to be broken down. In a problem like this, the thing that is fixed, such as the ground, even though I didn't put the hash marks into it, let's go ahead and do that. In a typical problem, you're not doing analysis on the part that is represented as stationary. We also have, so what we really care about in terms of analysis is A and B. In terms of the full force diagram, I expect you to be able to analyze the forces on everything. However, ultimately it's A and B. Now, one of the reasons I broke it down for you is the pulley separate? No, I want to treat the pulley as part of the ground. Matter of fact, that at this point. This rope here is an ideal rope. And an ideal rope has three major characteristics. An ideal rope is massless, so we don't need to worry about the weight of the rope. It is stretchless. So if I have A and B attached to the same rope, if B moves a meter, A is going to move a meter. That they will move the same distance. And it is frictionless. So I'm not worrying about the rope turning the pulley itself. The pulley is an ideal pulley. It is massless. And it is frictionless.
What about stretchless?
We assume that the pulley is not going to deform.
Okay.
But that's true for all these objects. We assume will not deform. Now, the massless and frictionless aspects of the ideal pulley and the frictionless aspect of the ideal rope, we will eventually do away with those. When I get to chapter 9, I think it is, we can handle that. Stretchless, it will remain stretchless throughout this course. And massless, 151, we keep massless ropes. How realistic is that? Well, no, ropes don't have mass. However, if the other masses, if mass A and mass B are significantly larger than the mass of the string or rope or whatever is being pulled there, then there are enough experimental errors that would drown out any errors caused by our assuming the rope is massless. All right, so I think I ran down this last time.
Yeah.
So what's the first thing we do?
Force diagram.
All right, so I've broken it up. Put down my checklist. And what, can we get rid of anything?
No, I don't think so.
Other?
Yeah, we can get rid of other.
But isn't there another box?
Yeah, there are two boxes, but I did not mention any additional mysterious
So
force.
no person moving it, for example.
Yeah. Yeah, or, hand of God. All right, so we got rid of one. That's pretty much it. Next. So what's acting on what? In which direction? struggle hearing right now.
No, sorry, gravity's pulling down on both boxes.
So force of gravity. If I done the,
Are we doing
did you say
W or
force of gravity or gravity?
gravity? He did.
Yep. Have I gone through that spiel yet? Gravity is a huge topic. We are concerned with very tiny aspects of it. We're concerned with force due to gravity / weight, the acceleration due to gravity, the gravitational constant eventually. But there are other aspects like the curvature of space and time because of gravity, et cetera, et cetera. So when you say gravity, that is this big topic here, and I only care about the one tiny part of it.
Force of gravity.
All right, so we have, I need subscript because I have more than one of these objects. But they come in pairs, is that the pair?
Nope, the boxes are also pulling up on the ground.
Okay. And again, I went with A and B because that's how I'll label the boxes, but some people will put just subscript 1 for the first one they do, and subscrict 2 for the next pair, and
Is
so
that a
on.
rookie mistake in this case?
Excuse me?
Is that considered a rookie mistake?
No, it's just,
Fact of life?
if you're doing a full analysis where you're actually calculating the acceleration, it becomes trickier if the subscript has nothing to do necessarily with that particular object, because then you have to keep referring back to, all right, what is this one again? So if I do A and B, I know anything with the subscript A has something to do with box A, anything with subscript B has something to do with box B.
Okay.
There's a hand up over there, someone?
For another force, the box A is pushing down on the ground.
What force is that?
Normal.
The one with the Y is normal, right?
All right, so why is it A? The other part of that pair?
The ground is pushing up on the box.
Gravitational force, done. Now, if this were a full force diagram and you did the down arrow on the rope for the weight of the rope, and then up on the ground, I wouldn't take off for that, I would just ignore it. There's another normal force pair.
Rope and B,
Excuse me?
the rope and box B.
Yep. I should say not necessarily. We don't know how the rope is attached to B, so we can't judge it. We lump that under something else.
Rope on the board. Rope on the board.
Yes. We have one other place of contact. We do have rope and pulley are touching each other. There's a reason the rope is bent like that, because there's some force in somewhere in that direction. Now, I did not give you enough information in order to know the exact direction of it, but I know that the rope touches the pulley here to here. So this arrow needs to be somewhere within that 90-degree range. So I just generically stick it somewhere middle-ish. And I got another one down here. So this is Y. I'll just do R for rope. And I don't do any forces between the pulley and the ground because I have drawn them as one object. And again, path to madness. If you want to do the forces between the pulley and the ground, then why not the top of A and the bottom of A, et cetera, et cetera. All right, what about B? Any normal forces on B?
No, it's not, if not on the rope, it's not pushing anything else, so no.
You said?
If not on the rope, then since it's not pushing anything else, then no.
Right. And that is a rookie mistake, is some people will do a normal force between B and the ground, despite the fact that they do not touch. Some will do B and the side here, despite the fact that they do not touch. All right, so normal force, done. Let's do friction. I guess tension is the new one, so let's do friction next.
We didn't okay, we have finished gravitational.
Yes, I have only two small objects with mass, A and B, and so I've got
I didn't see the check, that's all.
friction. Which way is friction acting on what?
So A is probably pulled, that box A is being pulled this way, so friction would be going this way.
On A?
Yeah.
Is that what you're saying?
Yeah.
I don't need a subscript because there's not gonna be friction on B. But if you put a subscript, that's fine. They come in pairs, where's the other one?
The other one will go this way on the ground.
Yes. Now, one of the criteria, necessary requirement for there to be friction is, we said contact earlier, more specifically, we need to have a normal force. If there's no normal force, there's no friction. So anywhere you have a normal force pair, that's where you need to check to see, is there friction here? Well, A and the ground, there's a normal force, so, well, we do have a friction pair there, there's gonna be sliding. And rope and the pulley, we have a normal force, but no friction because they're frictionless.
But there is tension.
And there is tension. All right, so, yes,
With friction, is there a specific way we need to point the arrows, or in this case, if they just pick a direction?
no, all right, so if you're looking from the ground's point, you're standing on the ground. Which way is A gonna go relative to the ground?
No way.
A, if I set
Which
this
way
up, would
is
you say
go-
A would go that way?
No, cause it's going towards the box B.
Yeah, so B is
If
gonna
it's
drag
being
this.
dragged towards box
Yeah.
B, then it goes this way, and the friction of the ground is going this way.
But, yours is the opposite.
So, okay, so.
This is what so from the ground's point of view, A wants to go that way.
No, because you know when you're on concrete and you scuff your shoes,
Yes.
and it feels like you're putting resistance on it instead of it aiding you forward. The ground is pulling you back.
And you're pushing it forward.
You actually push backwards. Or
Yeah, that's right. Yeah.
Are you looking at me or him?
not looking at him.
Okay.
Did that clear it up, or did you want me to?
I got it.
You got it? Okay. Other questions? All right, tension. Tension is a pulling force. I know that the rope is stretched because of tension. So there will be a tension at the end of each type rope.
Can I
String,
ask you a
chain, whatever.
question
Yes.
regarding tension specifically? It's going this way, towards each other. The arrows point each other.
Yes.
Is that B's relation to the point where it's taut? Or A's relation to the point where it's taut? Or is it like the rope itself?
I'm not quite sure I'm understanding the question because there's gonna be a pair between A and the rope and a pair between the rope and B,
Because in my mind, I'm thinking like tug of war.
okay?
And that's normal force in this case, but if there's tension, then there has to be a point where it's taut. And why would it be taut if you're pushing it towards each other?
You're pulling it towards each other. A is pulling on the rope that way. B is pulling on the rope that way. We are picturing this differently.
Yeah, clearly.
How about we put the tensions in and then ask the question again if it's
All right.
not clear? All right, as Robin said, the pair of tensions will be pointing towards each other. I know that at the end of each rope, there is a tension that's pulling on the rope. So I have a tension there, I have a tension here. It's parallel to the rope, it's supposed to be. But those are not part of the same pair. Because one of the criteria for the forces in a pair is they act on different objects, and those are acting on the same object. So, where's the other part of this pair?
Box A pointing towards the rope.
Yeah, it's what would accelerate the rope to the right. There's gotta be, if A could go to the right, there's gotta be something pulling on it, and that's it.
I get it. Never mind.
Okay. And what about B?
Pulling up to the floor.
Now, I've written in there with no subscripts whatsoever, even though those are two independent, well, those are two pairs. If it is an ideal rope, the tension will be the same at both ends. If it's not an ideal rope, then the tension will be different at each end. So if you want to put subscripts in there, then these two would have the same subscript, and these two would have the same subscript. In terms of analysis, when we get to the rotational motion, chapter 9, the tensions won't be the same at the ends, but at this point, we don't have enough information in order to differentiate them. Especially, it's a massless, stretchless, frictionless rope. There are no forces. The force here and the force there are the same. When we did the rope exercise in the hallway, at some point, I'm sure I commented that the tension, how much each person was pulling, was about the same. And it comes from that idea.
So, normal force is the ends of the same object pulling.
Normal force is a pushing force. Normal force keeps one object from going through another.
Can I put it on board?
Okay?
So I was thinking that, so that is that, which is what makes it diagonal. I was thinking that with this, it was from this point and this point, and those were going like that, and that's why I was confused.
The tension is pulling this way? Is that it?
That's what you were thinking was between this point and that,
Yeah.
and this point and that. I was thinking between this point and that point, pulling this taut,
Oh,
which is why I was confused.
yeah. Yeah, we're, because of our nice simplification over there.
There you go, SCR.
Because of our nice simplification, we don't have to worry about that at the moment. All right, let's just run down the rest of the process just to give you a taste of what's coming. If A accelerates, which way will it accelerate?
In the positive direction towards B.
Well, we haven't defined positive yet, so,
Right.
and towards B is a little bit vague. Because B's down here and
Is
A's
up
up here, it's not
considered
accelerating
north?
that way.
Is up considered north?
We'll accelerate.
We
to
could
the
just
right.
go with left, right, or
Yeah.
up, down.
Okay, right.
Accelerate to the right.
Okay. So A, if it moves, or if it accelerates, it'll accelerate to the right. So I'm just gonna draw a little arrow right here. This is not a force, it does not go in the force diagram.
So
I
should we
need
put
this-
like vector A?
Well, I'm gonna represent the direction by drawing an arrow, just writing a little A there. What about B? If B accelerates, which way will it accelerate?
Down.
All right, so I'm just over here, not part of the force diagram. The magnitude of those accelerations are the same. This goes with the idea that it is a stretchless rope. So they will move at the same rate, whatever it happens to be. So their accelerations will have the same magnitude, obviously different directions. So that's A. Now our coordinate axes. We set up a coordinate axes and we can have a different coordinate system for each mass. Now in this particular case, you might be able to get away with just a single one. However, excuse me, let's sort of think of them independently. I strongly recommend one of the directions of the I hat direction to be in the same direction as the acceleration. If you want j hat, that's fine too, but I typically do I hat. So I'm gonna set up a coordinate system for this mass right here, where I have I subscript A hat to the right, and then j hat is perpendicular to that. Up or down, it doesn't matter. I think you said down, all right? So there's my coordinate system for mass A. Mass B, let's set up a coordinate system for that. Since I chose I hat to be in the direction of acceleration for this one, I'm going to do the same here, except this will be I sub B hat. I could put in a perpendicular vector, but if I did that, I would end up with an equation 0 equals 0, which is a true statement, but not very particularly helpful. So that's the CA, the coordinate axes. Is once you establish the direction of acceleration, you set up the coordinate axes. D, decomposition. Do we need to break any vectors up? So we look at the forces that are acting on each mass, and we ask ourselves, are any of the forces not completely in the positive or negative I direction, or positive or negative J direction?
The rope's normal force on the pulley.
We are only looking at box A and box B.
Oh, I see.
Next to the downwards A acceleration arrow, next to box B, is that an I?
I hat subscript B.
Why is I now down?
Because we're.
It's a different mass.
Yeah, we want it to also be in the direction of the acceleration as well. At least for this.
Okay, so it's not of the entire graph.
Yeah, just
Right, no, I set up a coordinate system for each mass independently. All right, so if you look at the forces, are all the forces parallel or anti-parallel to my axes? In this case, yes. So we don't have to decompose any vectors. Now the equation of motion. Equations.